What you are looking at is a SymPy verification script executing exact rational arithmetic. We pass three distinct 3D coordinates into a degree 7 polynomial map called f. The inputs are 0, 0, -1/4, 1, -3 halves, 13 halves, and -1, 3 halves, 13 halves. Run the script, and all three distinct inputs resolve perfectly to a single identical output, -1/4, 0, 0. Then, the script calculates the Jacobian determinant of this map. The result is exactly -2, everywhere in the space. For 87 years, the Jacobian conjecture posited that any polynomial map with a constant, non-zero Jacobian determinant must be globally invertible. It asserted that every output would have exactly one unique input. The math we just executed breaks that assumption of global rigidity. We have a constant, non-zero determinant, yet three separate points collapse into one. The map overlaps itself globally. There are no numerical approximations here, no floating point errors. This is exact, verifiable mathematics. In less than 30 seconds of computation, 8 decades of assumed geometric rigidity are definitively falsified. The immediate question is topological. If the space isn't crushing or folding, how do three separate preimages merge into one? The inverse function theorem states that a non-zero Jacobian determinant guarantees local invertibility. Infinitesimal folding or the creation of a critical point is strictly impossible. Because of that local rule, the finite merging of any two preimages is mathematically forbidden anywhere in the entire 3D space. The map exploits a single loophole to change its fiber count, non-properness. Under a non-proper map, preimages don't collide in finite space. Instead, they are lost because they escape to infinity, while their target remains completely bounded. This 3D graph visualizes the mapping to a specific target plane, where c equals 0. The source space splits into two distinct sheets, a flat vertical plane and a curved multi-lobed surface. The flat plane maps perfectly bijectively, one point in, one point out. The curved surface holds the remaining preimages, covering that exact same target plane twice more. Watch what happens to the curved sheet as x approaches 0. The surface physically diverges, shooting upward toward infinity like 2/x². The flat sheet and the curved sheet never actually intersect at any finite coordinate. The counterexample slips past the inverse function theorem because the collision of preimages is brokered entirely in the unmappable bounds of infinity. To see how that escape mechanism is orchestrated, we have to look at the structural design of the degree 7 polynomial equations governing the map. The complex 3D behavior is driven by a hidden, weighted scaling symmetry. The x-coordinate does not dictate the underlying shape of the function. It acts merely as a scalar multiplier. The 3D target coordinates, a, b, and c, collapse into two invariant values, p equals bc/4 and q equals ac²/4. Because the map rescales its coordinates inversely, where x expands, c contracts, these specific ratios remain constant. The x-scale coordinate cancels out of the math entirely, isolating the two coordinates that define the map's shape. With the scale removed, the entire three-dimensional mapping problem collapses into a single one-dimensional cubic equation. This graph charts that specific equation, displaying the fixed cubic curve y equals w² minus w³. The p and q variables dictate the slope and height of an intersecting straight line. Generically, that line cuts through the curve at exactly three distinct points. Each of those three 1D intersection routes contains the mathematical DNA required to perfectly reconstruct one of the three 3D preimages. The map's impossible 3D behavior is an illusion. It is a simple 1D intersection problem, puppeteering the geometry from behind a veil of dimensional inflation. That 1D cubic curve is not a fluke. It is derived from a specific foundational seed polynomial, 2w minus 3w². That seed is simply the minimal member of a much broader mathematical framework known as a weighted lift construction. This graph illustrates the three rules any seed needs to work within this framework. It must pass through the origin, it must hit a specific negative target at 1, and it must have a net zero area. Plug a higher degree seed that follows those rules into the blueprint, and the framework generates a vastly more complex, yet fully functional, 3D counterexample. We can see this applied in an explicit degree 4 map we call map G, built from the cubic seed w-2w cubed. It requires massive integer coefficients and operates with extreme component degrees of 12, 11, and 4. Map G runs with a constant Jacobian determinant of -6 and possesses a generic fiber degree of 4. This graph shows map G's underlying 1D intersection. The target line now cuts across a two-humped quartic curve, isolating 4 distinct preimages. Because generic fiber degree is invariant under polynomial coordinate changes, map G is a mathematically distinct entity. It is not the original 3-sheet map wearing disguised coordinates. The initial degree 7 map was the first output of an engine capable of manufacturing paradoxes on demand. The underlying weighted lift framework introduced here works infinitely. By modifying the seed polynomial, researchers can predictably generate a unique, explicit 3D counterexample for any generic fiber degree n greater than or equal to 3. An infinite family of verified counterexamples now stands against 87 years of presumed global rigidity. Local invertibility tools, like the inverse function theorem, remain localized, failing to detect this class of algebraic evasion. If the Jacobian conjecture fails due to a simple non-proper escape mechanism, other assumptions in higher dimensional space may be resting on ghost topology. Verifiable mathematical truth in complex systems requires testing the extreme boundaries of infinity. Local behavior is an insufficient proof. I'm your host, and this is Synthiq Labs.